curved surface, irregular curved surface. For example, like this. Again, you can apply it. And then the same thing you have to watch out is where is normal at. And this is the curved surface. At any point, they have a normal. At this point, the normal is penetrate like this. And in this point, the normal go this way. So by you just draw a tangential line in here, a tangential line at that point, and then that defines the normal. So again, you use an incident ray equal to angle incident and the angle of refraction. The same thing with angle incident and angle refraction. Based upon this law of refraction, you can find out for a bathroom mirror, you only need 1/2 of the length of the height of the human, only half the bit length, then you can see a whole picture of the human being. Because this angle of refraction equal to angle incidence, we can apply this in a corner cube. So the corner cube basically is a three-sided mirror. One side here, three-sided mirror. With this three-sided mirror in an angle 90 degrees each to each other, then they form a corner cube. Each small corner cube will form. We are like to talk about the corner cube in the bicycle reflectors. All the bicycle reflector consists of bunches of corner cube. So using this corner cube of a bicycle reflector as a road sign, as an indicator, like your light at the back of your automobile. So that has been used quite well. So the law of refraction can apply to a lot of optical design, system design in mirror, especially about the large mirror. The one is called Hubble telescope, the mirror there, we're using them. The next we like to talk about is the law of refraction, in which case based on the Snell's law. This Snell's law basically we can tell is a mother of geometrical optics. Before we like to understand the law of refraction or Snell's law, we have to understand one important quantity called index of refraction. Index of refraction is related with the speed of light in vacuum and speed of light in different medium. The first one we like to understand the light travels at its maximum speed in vacuum. This speed is maximum per se in the vacuum. At that case, the C is a signal as a speed of light in the vacuum equal 3 times 10 to the 8 meters per second. As in this universe, this is speed of light in vacuum is the largest one. So light travels slower in dense medium. When the light travels in water, the speed of light reduces the speed. And when the light travels in the glass material, because the glass material are more dense than the water, so again, it will be travel slower. So more dense the material, they travel more slower. So in these cases, based on speed of light, we have a characteristic of material called index of refraction. By the way, index of refraction is depend on the different wavelength, So you usually N is index of refraction, the lambda considers the wavelength. We use N lambda to designate at that particular wavelength. The ratio between the speed of light in vacuum divided by speed of light in the medium at particular wavelength is C divided by B is equal to index of refraction. Because the speed of light is always larger, speed of light in vacuum is always the largest one. In these cases, index of refraction is always larger than 1.0. So this is one characteristic is very important. When somebody tells you the index of refraction is more than 1, you should question it. Is that true or not? Okay? Most of the time, the index of refraction cannot be less than 1. Okay. So we, one thing, there's some characteristic of index of refraction. One of the important characteristic of an index of refraction is index of refraction varies for different wavelength and for different material. For a particular material, the index of refraction versus wavelength is in this kind of a curve characteristic. Namely, it has the higher index of refraction in the ultraviolet light, and then the rate of change index of refraction are a lot faster. And then in the visible, the index of refraction changes is slower. And then the index of refraction changes in the infrared even more slower. Basically, the rate of change is gradually flattened. So for this, because of different index of refraction, it creating different wavelength, different color of light. When it enter a medium, it will spread out. Now, after we understand all this, that's why we define index of refraction at a particular wavelength rather than saying the index of refraction in general. Now, as far as Snell's law goes, is a very useful law. Basically, it's a law of refraction, the Snell's law. How we define it, again, is related with angles. Let's assume the medium 1 will associate with the index of refraction n1. Medium 2 associate with index of refraction n2. If this is a dense medium, and the instant light with the angle theta 1, when it go into the medium number 2 with more dense material, the light ray will bend toward the normal. But if the light comes from dense medium to less dense medium, from dense to less dense medium, the light ray will bend away from the normal. So if this is retraceable in this direction. So law of refraction says the n sub 1 times sine theta 1 equal to n2 times sine theta 2. This is basically related with the flat surface. Again, when you have a curved surface, you do the same thing. So for example, this is a curved surface. And then you have to define the normal. So the normal is going this direction. So if the instant light coming in this way, and it reflect. Okay? Again, using flat surface, curved surface normal as the point we're talking about. So this is related with the law of refraction. It's on page 8 on the blackboard. Page 9, we are talking about dispersion. In the book is section 25.5. So when the angle of refraction, when the light enters a material, depends on the lambda wavelength. That means the light, the white light coming in is going to be dispersed Disperse as far as it goes is from blue to red, have all different refraction angle. So this is called dispersion. At the section 25.6, the Huygens the principle, he assumed the light consists of waves rather than a stream of particles. Again, he based on the light travel as a wave, and he deduced the relationship called sine 1 times theta 1 equal to sine theta 2, the Snell's law. For that section of derivation, we want the student look at themselves, because that is a very good derivation, and then we like maybe put it in one of the examination problem. Please study hard on that, and if you have any question on that, please email me or call me about it. Thank you.